we've spoken already about work and we've spoken about energy independently. In this lesson, we're going to be looking at the conservation of mechanical energy. Now, before we talk about conservation of mechanical energy, you need to know the different types of forces. The first type of force we come across are conservative forces. But what is a conservative force? A conservative force is a force for which the work done in a moving object between 2 points is independent of the path taken. So it doesn't matter what the path direction is or how long it is, that work done is independent. So let's look at a couple of examples. So basically, the conservative forces are the ones that act over a distance, okay? In other words, they are the non-contact forces. So gravity, electric or electrical forces, and magnetic forces all act over a distance and are non-contact. So therefore, we know that these are the conservative forces by definition because the work done in moving the object is independent of the path, and that's very important. So obviously, if there are conservative forces, there must be non-conservative forces. So by definition, a non-conservative force is a force for which the work done in moving an object between 2 points is dependent on the path. So a conservative force is non-dependent, but a non-conservative force is dependent on the path taken. These forces are either called non-conservative forces or dissipative forces, and you need to know both names because they can come up either of them. So either dissipative or non-conservative. And dissipative means that it dissipates. In other words, it spreads out or it makes something lose energy, and that's what that force does. So if we think about it, conservative forces were the non-contact forces, then obviously your non-conservative forces are going to be your contact forces. So example are friction, air resistance, your tension, and any of your applied forces. So if you're in contact with something and you're applying a force, then it's a non-conservative force. But if the force is over a distance, if it acts over a distance, then it is a conservative force. And guys, you really need to know the difference between these and you need to be able to apply them. So please go learn this. It's very important. So now let's finally talk about what the theme of this lesson is, which is the conservation of energy and mechanical energy. Now, the definition of energy is that energy cannot be created nor destroyed, only transferred from one form to another. So if I ask you for the conservation of energy, just energy, okay, then we know that energy cannot be created nor destroyed, only transferred from one form to another. So in other words, the energy that was spread out when the atoms were made during the Big Bang, that's the same energy that is going around today. Now, mechanical energy of an object is a measure of its ability to do work. Okay, its ability to do work. So mechanical energy is a measure of its ability to do work. Therefore, mechanical energy is the sum of the object's gravitational potential energy and kinetic energy. Okay, it's the sum of its gravitational potential energy and kinetic energy. Now, there are two ways you can write your potential energy and kinetic energy. You can either write EP for potential energy, or you can write U for potential energy. And as we've seen in the previous lesson, your kinetic energy can either be written as EK or K. So therefore, E mechanical energy, E mech, is equal to EP plus EK, or we can write as EM is equal to U plus K, but it's the same thing. These are the same. It's just two different ways of writing it. You choose which way suits you. So now let's talk about the conservation of mechanical energy. Now the definition says when only conservative forces are present, mechanical energy is conserved. So when only conservative forces are present, mechanical energy is conserved. And remember, what were the conservative forces? They're the ones where it doesn't matter what the path is. It doesn't matter which path it takes, So it's the non-conservative non-contact forces, Okay, right. So we need to understand this. When non-conservative forces are present, okay, so that would be your contact forces, like your force applied or your friction. When they are present, mechanical energy, which is the sum of the kinetic energy and potential energy, is not conserved, okay? But remember, the total energy of the system is still conserved. So therefore, the total energy of a system is always conserved, right? But the mechanical energy is only conserved when there are only conservative forces present, okay? So we now know that EMEC is equal to EP plus EK. And EP is the gravitational potential energy. So let's talk a little bit more about gravitational potential energy. This is the energy an object has due to its position in Earth's gravitational field. Makes sense? Gravitational potential energy is the energy of an object has due to its position in Earth's gravitational field. In other words, we're saying really, how high is it? The definition of that gives you this formula where EP, which is the gravitational potential energy, is equal to mass times gravity times height. Okay, so let's just think about that. We know that net work done is equal to F delta X. But this work is now the work done by the gravity. Okay, by gravity. So therefore the force that we're talking about is the force of gravity times by the displacement. And the force of gravity is always mg delta x. And that's where that equation comes from. The potential energy due to gravity, gravitational potential energy, is equal to the mass, which is always measured in kilograms, times the acceleration due to gravity, which is in meters per second squared, times by the height above the Earth, the delta x, the displacement. The height above the Earth always in meters. Okay. So an object obviously gains gravitational potential energy when it is lifted up into the Earth's gravitational field. So the higher the object is above the Earth, there's the Earth, really badly drawn Earth, above the Earth, the more it has. So EP is more when the object is higher, and over here the EP is less. Why? Because the mass of the object is not changing as we travel up and down. The acceleration due to gravity basically doesn't change. So therefore, the only thing that's affecting our energy due to gravity or potential energy is the height, which is either very small or very big. So the higher we go, the more the potential energy. Now, if we recall, we said that EMEC is equal to EP plus EK, right? So we've spoken about EP, which is the gravitational potential energy. Now let's talk about EK. Now EK is the kinetic energy, and this is the energy an object has due to its motion. Kinetic means moving or motion or of movement. So that's why we say that kinetic energy is the energy of an object due to its motion. And as we know, EK is equal to half mv squared. Half times mass times velocity squared, where m is mass in kilograms and v is velocity in meters per second. Guys, it's very important that you get your units right. Right, now let's talk about the conservation of mechanical energy during free fall. So here we've got a little girl, and she is holding a ball, and what she's doing is she's going to drop this ball. So let's talk about the mechanical energy during the time that she drops this ball. So we talk about the mechanical energy of the ball. So we know that EMEC, mechanical energy, is equal to EP plus EK, or is equal to U plus K. Okay, and we know that EP equals mgh, and the kinetic energy is a half mv squared. Okay, so as this ball is dropped, okay, so as it is moving down, okay, let's talk about what is going on. Since it is dropped, it has initial velocity. The initial velocity is 0. So therefore, its EMEC is equal to EP plus EK, which is equal to mgh plus a half mv squared. But there is no velocity. So therefore, the total mechanical energy at the top of this distance, if the ball is dropped, is just equal to the mgh, which is equal to EP. Okay. At the bottom, when it hits the ground, or just as it hits the ground, your EMEC is still equal to EP plus EK, okay, which is equal to mgh plus a half mv squared. Now, if you think about this, it has no height. Therefore, this time, the mechanical energy does not have any potential energy. It's only got kinetic energy. So the total mechanical energy is equal to the kinetic energy at the bottom. Now let's talk about as it falls. Okay, so as it falls, let's make it a little bit easier before we talk about how it falls all the way. Let's talk about halfway. So as it's falling at halfway, what has happened is the height has become half the height. We're now looking at half the height, and that obviously is a full height. Okay, at that point there, it's half the height. So therefore, EMEC, remember that it's conserved, is equal to EP plus EK. But now the EP is is mg times half the height, okay, plus your EK, which means that therefore this is a half EP, which means that what has EK got to be? EK over here was 0, okay, but now the EK has to equal a half EP. So therefore, we can see that the EK has got to have gone up. So what am I trying to say with this? I'm trying to say that at the halfway point, the potential energy is going to be half the potential energy up there, and the rest of the energy has transferred to kinetic energy. So therefore, the mechanical energy is equal to, again, EP plus EK, where yeah, your kinetic energy was 0, yeah, your kinetic energy is a maximum, whereas yeah, the potential energy, all the energy is equal to potential energy, therefore this is a maximum. Over here, there's no potential energy, it's 0. And as you travel down, the potential energy is going to be going down, and the kinetic energy is going to be going up, so that it is being continually transferred, so that EMEC, the total mechanical energy, remains the same. But this, of course, can only happen during free fall. And what is free fall? Free fall is when you're falling under the force of gravity, which is a conservative force, and there is no other force acting on it. During free fall, we assume that there is no force of friction due to the air. In that case, your EMEC is always going to equal to EP plus EK, and your EMEC is conserved. And that, grade 12s, is how the conservation of mechanical energy works. And we are going to, in the next lesson, go through a whole bunch of examples so you can understand how to do this.